Alright, thanks for watching. And today I would like to talk to you about the different definitions of diagonalizability, one of the longest words in the math language. And I want to also show you that they're equivalent. So, what is the main definition of diagonalizability? It basically means you can turn a matrix or a linear transformation into a diagonal matrix. So this is like the primordial definition of diagonalizability. So suppose your vector space is finite dimensional, and suppose that you have a linear operator. So T from V to V, it's a linear transformation. Then we say that T is diagonalizable if and only if there's some matrix, so some basis for which the matrix of T is diagonal. So if and only if there is a basis beta of V such that the matrix of T is diagonal. And in some other video, I give you a concrete example of how to find that basis and in fact that this matrix is diagonal. And so again, diagonalizable means you can turn it into a diagonal matrix, but the question is, what does it have to do with eigenvalues and eigenvectors? Well, it turns out that diagonalizable means the same thing as find a basis of eigenvectors. So here's the first fact. So T is diagonalizable if and only if there is a basis beta of V. So I guess a basis beta of V where beta consists of eigenvectors of T. In other words, a linear operator is diagonalizable if and only if you can find a basis of eigenvectors of that linear transformation. And in fact, this is how you can also define diagonalizability in infinite dimensions. Because technically for matrices, it only works for finite dimensional vector spaces, but basis of eigenvectors, that's also true for infinite dimensions. So, why is that true? Well, let's see. Suppose T is diagonalizable. Then what do we know? Then we have a basis such that the matrix is diagonal. Then there is a basis beta, let's call it V1 up to Vn of V, such that this matrix T beta beta, no d beta about it, okay? It's diagonal. And in particular, what it means is there's some matrix with diagonal entries where, let's say, the diagonal entries are d1 up to dn. Up to dn. And there's a main reason I did this video because in general, the jth diagonal entry of this matrix, it's called dj. So dj Peyam in the house, we have that. Now, I'm claiming that this beta works. In other words, I'm claiming that this beta is a basis of V, which we already know, that consists of eigenvectors of T. And let's show that this is true. So claim beta up to V1 up to Vn consists of eigenvectors of T. Because so far we don't know that we have eigenvectors, but let's just remember how to define the matrix of a linear transformation. What this means is that to find a matrix of T, you evaluate T at every basis vector, T of V1, T of Vj, T of Vn, and you express it in terms of V1, Vj, up to Vn. So, by definition of the matrix of T, so by definition of T of beta beta, we know that if you evaluate T at Vj, you get 0 V1 plus 0 V2 plus dot 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 plus dj, turn it up. So dj Vj plus dot 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 plus 0 Vn. In other words, T of Vj equals dj Vj. Lots of Vj's today, and j is from 1 up to n. But what does that mean? If T of Vj is dj Vj, it means Vj is an eigenvector of T. Of T with eigenvalue dj. In other words, this basis beta of V is a basis of eigenvectors of T. And therefore we're done. Alright, what about the other direction? Suppose there's a basis of eigenvectors of T. Let's show T is diagonalizable. Well, it's literally just the converse of this. So in other words, let beta be a basis, I guess that's right, as V1 up to Vn. Be a basis of eigenvectors of T. Of T. What does that mean? It means that for every j, T of Vj equals to lambda j Vj for some eigenvalue lambda j, which is in your field, so some scalar real or complex number, for example, or other fields in case you're interested. Then let's calculate the matrix of T. Then for this beta, well, again, to calculate the matrix of T, all you do is for every vector, you calculate T of that vector, I guess T of Vj, and you express it in terms of V1 up to Vn. So what do we know? T of Vj, by definition we know it's lambda j Vj, but if you express it in terms of V1 up to Vn, it's 0 V1 plus 0 V2 plus dot 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 plus lambda j Vj, precisely in the jth entry, plus dot 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 plus 0 Vn. So what this means, if you take the jth entry of tvj, you get lambda j, and everything else is 0. So in particular, for the T of V1, the first entry is lambda 1. Everything else is 0. For T of V2, the second entry is lambda 2. Everything 0. and up to lambda n, where everything is 0, up to the last one. So what do we know? T, the matrix of T with respect to this basis, it's precisely diagonal, with the diagonal entries being the eigenvalues. So, in other words, what did I prove? I proved that, well, if there's some matrix for which T is diagonal, then basically the corresponding entries are the eigenvalues, and if you have a basis of eigenvectors, then the matrix of T with respect to that basis is diagonal, with the diagonal entries being the eigenvalues. So that was one thing, one very useful characterization of diagonalizability, and this is why you always, to figure out if something is diagonalizable, you have to find the eigenvalues and eigenvectors. So, that said, this was for more general linear transformations. What about for matrices? Well, it turns out there's an even easier characterization of that that's very useful in practice. So, just a little definition. So, for matrix, A is diagonalizable if and only if a corresponding linear transformation is diagonalizable, and that linear transformation, because we're in SoCal, it's called LA, but not really, it's called LA because it's left multiplication by A, or left multiplication by A goes from Fn to Fn, and it's literally multiplication by A. So LAX, worst airport in the world, is AX. And in particular, what does that mean? So it means that there is a basis for which there's a basis for which LA is diagonal, but also there exists a basis of eigenvectors of LA, which is the same thing as saying there exists a basis of eigenvectors of A. Because if, let's say, LAX equals to lambda x, this just means AX equals lambda x. So if x is an eigenvector of LAX, then x is an eigenvector of A. So if and only if there is a basis of eigenvectors of A, which is a much more useful characterization than just saying LA is diagonalizable. Because what does that mean for LA to have some basis for which the matrix is diagonal? It's much easier to understand that there's a basis, of Fn of eigenvectors of A, where A is n by n, if you want. Alright, that said, for matrices, there's an even more useful characterization, which I like to talk about. And it's probably the one you heard before. It's with this, PDP inverse or QDQ inverse. So here's the second fact from today. So A is diagonalizable if and only if A equals to QDQ inverse, where D is diagonal, and Q is invertible. And let us show why this is true. Alright, so suppose first of all A is diagonalizable. A is diagonalizable. then let's not use actually the statement of eigenvectors. Surprisingly, you have to use the statement about LA being diagonalizable. Then T equals to LA is diagonalizable. Which means that, again, there is a basis beta, if you want, of Fn, for which the matrix is diagonal. So T beta beta is diagonal. And for a second, let's not change bases, and you'll see why this is useful. So which other basis of Fn can we pick? Well, why not just the standard basis? Because it's the standard one. So let gamma be the standard basis of Fn. And again, it's just, for example, in R3, it's 1, 0, 0, 0, 1, 0, 0, 0, 1. So just the standard one, and there's a reason why this is useful. Because we're given this matrix, right, which is diagonal. Now, we would like to find the same linear transformation, but with respect to a different basis. Fortunately, there's an easy way to do this. So let's calculate T gamma gamma. So, and luckily, as I said, there's a video I've done on this, where you can just change matrix using a very easy thing called the change of coordinates matrix. So by some previous video, we know that if we simply change the basis here, it's easy to figure out T gamma gamma in terms of T beta beta. So T gamma gamma equals to Q T beta beta Q inverse. Where Q, what is it? It's simply the change of coordinates matrix from beta to gamma. Okay, why is that useful? First of all, Q is an invertible matrix, and again, we know that this is diagonal, right? And let's just figure out what this matrix is. So with T equals to LA, we get LA gamma gamma equals Q T, so I guess LA beta beta Q inverse. And we know, again, by assumption that this is diagonal. So let's call this D. So what we get is LA gamma gamma equals Q D Q inverse. And last but not least, what is LA gamma gamma? Well, to figure out LA gamma gamma, just evaluate LA at each of the standard basis vectors. But remember, what is LA, for example, of 1, 0, 0? That is A times 1, 0, 0. And if you calculate that, let's say, for example, 1, 2, 3, 4, 5, 6, 7, 8, 9 at 1, 0, 0, that gives you precisely the first column of A. So LA of 1, 0, 0, it's 1, 4, 7, that's the first column of A, and in particular the coordinates with respect to gamma are still 1, 4, 7. LA 0, 1, 0 gives you the second column, LA of 0, 0, 1 gives you the third column, which means in the end, if you use a standard basis, the matrix of LA, it's simply A. So what we get at the end is simply A equals to QDQ inverse, which is wonderful. And this is precisely why we use the standard basis, because the matrix of LA is easy to calculate with that standard basis. That's on the one hand, and now let's do the other direction. So suppose we know that A equals to Q dQ inverse. Show that A is diagonalizable. And in this case, we want to use the eigenvector approach. So goal, find a basis beta, which is V1 up to Vn, of Fn of eigenvectors of A. Right? Okay. And how can we find that basis? Surprisingly, they're given by the columns of Q. So we know that Q has column vectors V1, V2 up to Vn. Claim this beta works. So beta is V1, V2, Vn works. Where Vj is just the jth column of Q. And what do I want to say? Yeah. Forgot what I want to say, but hopefully I'll remember it soon. All right, first of all, why is this a basis? Precisely because Q is invertible, so you can show that a matrix is invertible if and only if its columns form a basis for Fn. I guess in general Fm, but here we have a square matrix. And let's see what this decomposition has to do with eigenvectors. So if A is Q dQ inverse, well, let's multiply A by Q. So AQ is Q dQ inverse Q. Such a cutie. And Q inverse Q is the identity, so AQ equals to QD. It's almost like QED, but with just a QD. And what is Q? Q has vectors, column vectors V1 up to Vn, and again V1 up to Vn and D. And let's say the entries of D are lambda 1 up to lambda n. Not eigenvalues yet, but you'll see that it is true. Now, remember that if you multiply a matrix by a bunch of vectors, there's kind of like a foiling property happening. So we get AV1 up to AVN equals to, what about here? It turns out there's a similar distributivity property going on, and let me just illustrate it with one example. If you do 1, 2, 3, 4, and you multiply by 5, 0, 0, 6, then if you do that, what you get is 5 times 1, 5 times 3. So 5 times 1, 3, and 6 times 2, 6 times 4, 6 times 2, 4. So indeed, if you multiply a matrix by a diagonal matrix to the right, it's like multiplying every column by the diagonal. So we indeed get, this is lambda 1 V1 up to lambda n Vn. All right, so that's good. In other words, what do we get? The matrix AV1 up to AVN equals lambda 1 V1 up to lambda n Vn. And lastly, we just need to compare the columns. And what you get is AV1 equals lambda 1 V1. In general, AVJ, it's lambda j Vj. Up to AVN, it's an avian species, lambda n Vn. In other words, what do we have? We have that indeed beta, again, is a basis of Fn, and it consists of eigenvectors of A. So surprisingly, if we have this decomposition, A is Q dQ inverse, we indeed get that the columns of Q are the eigenvectors and that the entries of D, like the diagonal entries of D, are the eigenvalues. So it turns out this thing has a lot of info also about the geometry of A. Alright, I hope you liked this little video. If you want to see more math, please make sure to subscribe to my channel. Thank you very much.